Hello, everyone. Slight technical difficulties now fixed. My name is Scott Grizzard. This is Calculus Fall 2020, Calculus 1. My name is Scott from the University of South Florida. Last time we talked about L'Hopital's rule. Tonight, what we're going to do is we're going to talk about constrained optimization, which is kind of the big theme. One of the two big themes. So there were two kind of sections that make up Module 2. That's kind of the whole point, the thing we're driving toward. One of them is 4.4, which is derivatives in the shapes of graphs. So we've been going over derivatives in the shapes of graphs during the interactive class time for the last 3 weeks, right? We had a problem set that talked about the second derivative. Then we had a problem set that talked about visualizing. You know, we had pictures of the first derivative, and we wanted to say things about the original function. And then for this week's problem set, we have talking about, we've got an algebraic representation of a function, and we want to take derivatives, and then we want to solve for, find out where the derivative is positive, where it's negative algebraically. And then we are going to, be able to tell where the inflection points are, where the mins and maxes are, and all of those things. But tonight, let's go back. Let's start talking. So we're going to talk about that more on Thursday as a formal lecture. But again, we've been talking about that section for the last 3 weeks, with last 3 problem sets, including this week's. Tonight, what we're going to do is we're going to focus on the other big thing, which is optimization. So we have this method, okay? We have this method that if we have one equation, we can find the optimum. Okay, so let's look at what that looks like. So if I have one equation, let's say that equation is, we want to, save all this stuff for later. Suppose that I have one equation. I want to maximize x squared plus 10 on the interval -2, 1. So suppose I want to maximize the max of, okay, now it's working. Okay, so I already know, now that, the fourth time, right? The microphone wasn't working, and now, teaching online adventures. Let's try this again. I already know how to find the maximum of something on a closed interval. Wait a minute, you still can't hear me? I just fixed that. Okay. Suppose I want to find the maximum of a function on a closed interval. And I already know how to do this. But let's say it's like x squared plus 10 on -1, 3. Right? So what do I do in order to find this? So what I do to find this is I take the derivative, right? So what do? I take the derivative, set it equal to 0, and find the critical numbers. Right? So let's do it. So we do d over dx of x squared plus 10 equals 2x plus 0. And 2x equals 0 implies that x equals 0. All right, and then I check my endpoints as well. Endpoint, so the x's to check are my critical numbers, 0, -1, and 3. Okay, and I have this idea, right? I already know what the picture is going to look like. Stop that. All right. So in one sense, I already know what the picture is going to look like, right? I'm going to have did it again. I'm going to have something that looks like this, right? I know that's what it's going to look like, but let's just do it. Sorry, what did I want to do? I wanted to find the max or the min. I want to find the min. Sorry, the max. See what everything happens when it's wrong here. So I want this to be the max of negative x squared plus 10. So you see what happens when things go wrong. Just everything just goes. Okay, but this is still negative 2x, right? Negative. There we go. So now I want to find this maximum. And I already know what it's going to look like, right? The max is going to happen at 0. But let's just throw it in here. So I've got negative x squared plus 10. So this is going to equal, so f of 0 equals, in my original equation, 0 squared, negative 0 squared plus 10, which is going to equal 10. F of negative 1 equals negative 1 squared, negative 1 squared, negative 1 squared, plus 10, which equals negative 1 plus 10, which equals 9. And f of 3 equals 3 squared, negative 3 squared plus 10 equals negative, negative 9 plus 10 equals 1. So the max is y equals 10 at x equals 0. So 1 to 5, how do we feel about that? Now that things seem to be working and I seem to have the right equation here. And we already know that it's going to look like this. Right, we have this idea from pre-calc that the max is going to happen at the vertex and that's going to be at 0. Okay. Now, most of the things that I want to optimize for in real life have this same type of problem. There's kind of a natural endpoint of some sort, but we usually get them in terms of two equations. All right. So this is one variable optimization. It's really two variable optimization, but what we're doing is solving for one of the variables. Okay. So we can apply this method to real world problems. And the trick is to set up the equation. Okay. So let's look at this one. I typed this out at advanced. Suppose we want to build a fence to enclose some rectangular area. Okay. So I want to build a fence and I have enough material to build 80 feet of fence. So my linear feet of fence is 80. So I've got this situation, right? What's the largest rectangular area I can enclose in this fence? So what is the largest rectangular area I can enclose in 80 feet of fence? So I have this idea that I'm going to have something that looks like this. Okay. And I've got some equations here, right? I've got area equals length times width. So I know that I've got this idea that I'm going to have some width here. I'm going to have some length. Okay. And I want this to be as big as possible. And I know that I've got 80 feet of fence, right? So this is going to be L, this is going to be W. And I know that L plus W plus L plus W equals 80. So how do we feel about that? 1 to 5. It's kind of this largest rectangle I can build. So I want to maximize A given what I have. Okay? So this is going to mean, this constraint here is going to mean that 2L plus 2W equals 80. I'm going to subtract through by, I'm going to divide through by 2, and I get this. Okay? All right. So let's see what happens here. Just as a thought, I don't know a lot of math. So how can I get at this? Well, let's do something, psycho. Let's go ahead and throw it in a little, let's give a little naive try here and throw it into a little spreadsheet. Okay, I know a little Excel here. We're not in business calculus, but so whatever my length is, I know that my width is 40 minus whatever that length is. So if I choose all width and no length or height, I'm going to wind up with no area. And likewise, if I choose length of 40 and a width of 0, I'm going to wind up with no area. Okay? So how do we feel about that 1 to 5? Right, so by the way, these right here, I've got a formula here in this thing. It's 40 minus A2, and then I choose A2 times B2, and of course I filled down. All right, so I'm going to wind up with this thing. If I, let's see how I can do this, if I remember how to do this. It's been a while on the Excel. Oops. So if I want that one too. I lost it. Okay, that one and that one. So it's been a little while on the Excel, but I remember there was something called like a chart thing here. So what I wanted to do, this looks like I want one of these, right? So if this right here is the length at the bottom, if I put my length as the dependent variable, and this is my total area that I'm going to get, it's going to be when I'm going to maximize this when I've got 20 here. But this looks like a nice little differentiable function now, doesn't it? So how else can I do this? How can I make this appear? Well, the answer is here. I solved for length on the bottom, in a sense, and then I put that in an equation for area. So what I've done here is the following. I need to combine this to one equation. Okay? So what I do, and I'm going to do some terms here that I'm just going to keep. Okay? I'm going to have output is going to be the thing that gets bigger. And I'll tell you what I mean by that one. And I'm going to call cost whatever the resource is the resource I'm using. Things that get big, that's kind of vague. Let's do we'll come up with a better thing. Right now, my area is my output, and my cost is kind of this. It's perimeter, but I don't want to think about it as perimeter, because perimeter is kind of specific to a thing, a particular problem. I want to think of it in terms of cost. And I kind of want to make this my motto. Things cost money. All right? Now, or cost something. It doesn't have to be, they cost building materials in this one. So here I've got a cost equation and I've got an output equation or production equation. Okay? This is kind of the output. This is the thing here. And what I want to do is I want to maximize, the problem is to maximize output A given cost equation. L plus W equals 40. Okay, so the idea is, no, it's not actually cost, and this is not really output, but I want to think of them in those terms, because that's slightly more generic than thinking about perimeter, which is, because that's not really what's going on. It's not perimeter that I want to, that's my constraint. I mean, it is, but there's something more generic, right? Cost would be something that could go from problem to problem. So 1 to 5, how do we feel about that? So what I'm going to do is I'm going to, and output's the one I want. So I want to max output given cost. Okay, that's the idea. I want to max output given cost. So what I'm going to do when I want to max output given cost is I'm going to solve the cost for one variable. And then plug it into the output equation. So what I have here, and again, I'm trying to like talk about this particular problem, but I'm trying to think in slightly more general terms. Okay, so what I'm going to have here is I'm going to have L plus W equals 40. Now I'm just going to pick one. That means that L equals 40 minus W. There was no real reason to pick L. I could have picked W. Sometimes there's a reason I want to pick one over the other because the algebra comes out nicer. But, you know, I'm just fine with that. And now I'm going to sub it in here. So I've got A equals L times W equals, and now I'm just going to sub in here for L. So I've got 40 minus W times W. Okay. Which equals 40W times W squared. 1 to 5, how do we feel about that? Okay. So now I have something I can maximize. Now I need to kind of think about what the endpoints are. Okay? Does it make any sense to have negative fence? No, right? Fence is a positive thing. So I've got endpoints, right? My endpoints, negative fence makes no sense. Negative fence makes no sense. Right? So the endpoints are going to be, right, it makes no sense to have a negative amount of fence. So my endpoints are going to be L equals 0 and W equals 0, which is going to give me W equals 40 and L equals 40. So these are kind of my endpoints. Okay, so I've got these, you know, it doesn't matter. Here I'm going to be using W, so I'll use the two W endpoints, but I could use the L endpoints. It doesn't matter. Okay. So now I'm going to take the derivative and set it equal to 0. Okay, how do we feel, by the way, about this? 1 to 5. This kind of I want to mention the endpoints that make sense. So now I've got my endpoints won't always be these nice little 0 and 40. Sometimes they can be infinities. But it'll be pretty clear that what you've got is that. All right. Now I take the derivative, I set it equal to 0. I solve for my critical values. So here I've got A equals 40W. This should be a 40W. I can't do math tonight, apparently. Minus W squared. Sorry about that. Minus W squared. That means that dA over dW equals 40 minus 2W. Okay. So that means if 0 equals 40 minus 2W, that means that 2W equals 40. That means W equals 20, as we expect. 1 to 5, how do we feel about that? Right, solve for the critical values. Okay. Now, don't forget, we need to plug in the endpoints. So we need to check the endpoints. But let's solve for L real fast. So I've got W equals that. Now I've got my constraint equation here. L plus W equals 40. And these are in feet, right? Okay. So area of 20, or area when W equals 20, I could just write that. The area when W equals 20 is 40 times 20 minus 20 squared. I'm going to factor out a 200 here. And I'm left with 4 minus 2. That's certainly easier to do. Instead of messing with all those things, I just factored out a 200, and then I solved. Right? I did that right? Yes. Okay, and this is in square feet. Okay, people say I keep freezing. Frames missed or rendering lag 0. Skipped frames due to encoding lag 0. Dropped frames by the network 0. My up bit rate is 5.8 megabits per second. 2 twid. I don't see where the I'm sorry I seem to be freezing and dropping frames, but it's your fault, not mine right now, according to my system. Okay. I'm going to keep going then. As long as it's not encoding lag on my end, you'll be able to see it on YouTube later. Anyway, I'm sorry you're having drop frame issues. Okay, so I've got this, and now I need to check my endpoints. So my other options are area when W equals 0, which equals, 0, and area when W equals 40, which equals, let's see, 40 times 40 minus 40 squared, which equals 0. And obviously 400 is the bigger of those. Now, I need to do something to check that I have a max. Now here, I get away with it. Okay? Now here, I can get away with it nicely. Okay? Because I only had one critical value, and I checked the endpoints. So here I can justify it very simply. I don't need to do a second derivative. I don't need to do a first derivative test. Here I just say, I've actually done it already. Right? Here I just say, since I only have one critical value, and that one is bigger than the endpoints, I have a max. 1 to 5, how do we feel about that little gesture? I have to make a little gesture. Okay? I need to do something to show that I have the max. I either need to check all my endpoints, which you should be doing anyway, or I need to take I need to, compare the left and the right sides with the first derivative test, or I need to do a second derivative and find out that it's concave down, in which case, I've got it. So I need to make a gesture. And then I do the same thing that I did when I had the related rates problems. Okay? Then, like the related rates problems, state what you mean. So, what I mean is that if L equals 40 feet and W equals 40 feet, I maximize the area of the fenced-in area. I maximize the size of the fixed-in area, I guess. Area at 400. Was it 40 feet or 20 feet? 20 feet. At 400 square feet. So I just kind of finish it off like I did the other ones. Okay. 1 to 5, how do we feel about that problem? And just make sure that I answered it, right? What's the largest area that I can be enclosed in that 80 feet? Well, it's 400 square feet. Okay, so that's the idea. I have these two things going on, and I kind of just throw them together. I try to make one equation, and then I just have a min-max. I have a min-max problem. Okay, I have the same problems I've already been doing. But I got to get them there. So I need to force everything into one equation, and then I have a min-max problem with some details, right? I have to use some, so I draw me a picture, kind of like I did with the related rates. I kind of solve it, figure out what's going on, and then I take a derivative. I set it equal to 0. Okay. Well, there's a flip side to this. Suppose instead I wanted to minimize. So, new problem. Suppose with the same suppose I wanted a rectangular area of 400 square feet. How much fence do I need? I can't spell fence. So now I've asked a slightly different question. Before I was given the constraint, the cost, right? I was given the amount of material available, and I found the largest area that could be enclosed. Now what I want to do is I want to build a certain amount of area, right? Now I've got a fixed output, and what I want to do is minimize the cost. Okay, so 1 to 5, how do we feel about this little change in setup here? Okay, so how could I get at this? I've got a fixed area, right? Let's see. I know I want a fence. And I know it's going to have some length and some width. All right. And I know that the area equals A equals that L times W. And I know that my cost, and I'm just going to call it C. Yeah, it's my perimeter, but I'm going to call it my cost. Just because it's the thing that I'm always kind of doing here. And I could call this Q. If I wanted to be consistent across the board, I'd call this Q, my quantity. But whatever. Cost is the kind of thing. I need fencing for this, and I need this. So I got 2W plus 2L. Just as I kind of did before. Except now this is a variable. Okay. Well, how would I set this up in Excel? Right? I've got area, and I've got length, and I have width. Now, how would I set this up into Excel? Well, let's see. I know whatever my width is, I know I'm going to need, let's look at this equation here. I know I'm going to need 400 feet squared equals L times W. So I've got this type of idea that 400 over L is going to equal my W. So whatever my L is will actually determine what my W is. So here the area needs to be, so here what I'm going to have when I plug it into Excel here, let's make this happen here. So here's Excel. Zoom it in a little. All right, so my area is always going to be 400. My length, I don't know what that's going to be. We'll call that my independent variable. But whatever that is, 400 divided by L is the width. And of course, it's going to give me a divide by zero error here, but that's okay. Equals 400, we'll just put in that one, divided by that one. And then what I'm going to do, in order to get the total fence needed, I'm going to have equals this plus this. All right, and let's say I go, let's start this at 400. Okay, so if I did a 400 by 1, right, if my width was 400, if my length was 400, my width would need to be 1, and I would get an area of 400, and I'd need 401 feet of fencing. 1 to 5, how do we feel about that? Oh, this should be 2, I'm sorry. So this should be 2 there and 2 there. Oh, and you can't do that because you need asterisks. So this should be 2 times B2, and this should be 2 times C2. Okay, so I need 802 feet of fence. Okay. Well, let's see. Let's say I did my length. Let's get a little bit, ambitious here. Let's make this 400 all the way down. Let's make this whatever this. Let's, copy down here. Right? And on the other side, let's say I do 40. That seems a little bit more reasonable. Now, if I do 40, I only need 10 feet of width. And that means my total fence needing is now 100. All right, well, let's do 35. Well, that's good. 30, 25, 20, 15, 10, 5. Eventually, I'm going to go to badness, so I want to make sure I don't do that. What the heck? And if I've got 0, so if I did 2... Let's do 3, 2, 1. Okay. So I have this idea that I could do 1. And you see how I need like tons of fence? So let's do this. Let's do a little graph. Insert. Chart. That one. So there's type of my total fence needed, right? So this is the amount of length I have. That's my independent variable. And then this is the total fence I would need given this. Okay? So 1 to 5, how do we feel about that? And I can tell that there's a min here. It happens to be at x equals 20, but it's way down here. And I can already tell that I'm not going to care about these endpoints. Okay. So how do I go about solving this? So it's kind of the same thing. Here I've got my constraint equation, and I'm going to plug this into C. So C is now equal to 2 times 400 over L plus 2 times L. And that 2 is just annoying me. But I don't want to get rid of it because it's over there. Now I'm going to take the derivative and do what I did before. So dC over dL equals, this is going to be 800 over L. So this is really the derivative with respect to L of 800 times L to the negative 1 plus, that's just 2. So this bit right here is going to be the derivative with respect to this is going to be 800. So I'm going to get negative 800 times L to the negative 2 plus 2. And I'm going to set that equal to 0. So I get, and I'm going to set that equal to 0. So I get 0 equals negative 800 L to the negative 2 plus 2. That just kind of hangs out. It's an annoying little 2. So that's going to give me that 800 over L squared equals 2. Let me just make sure I did this right, because those numbers don't look like they're going to make me happy. Oh, they will. Okay, good. That means that when I multiply this over and divide this, that means 400 equals L squared. Now, that means that the square root of 400 equals L. Why do I not need the plus minus there? And you know what I'm going to do? I'm going to move this over here because that's just annoying me. Okay, so how do we feel about that 1 to 5? What I did was I took the derivative and I solved it for 0. So here's a critical value. Now, the endpoints. Well, any amount of positive fencing makes sense. So my endpoints are L equals infinity and W equals infinity. Okay. Well, you may think that's bad, but that's actually good, right? So here, if L equals infinity or W equals infinity, I need an infinite amount of fence. And that's silly, right? So what this thing looks like, based on this little fact here, is something like this. And I only have one critical value. Might be okay with that. I got infinite endpoints and only one critical value where I've got a finite number, right? So it's got to be that L equals 20. Right? If that doesn't make you comfortable, look at the derivative. Okay? So I've got DC here, right here. So DC over DL, when L equals, there's my critical value. Okay. Pick something on the left, then pick something on the right. Okay, well, when L equals 10, here's what I'm doing, by the way. Here's F. Here's F prime. Okay, so here is L equals 10, L equals 20, and we'll pick another one, L equals 30. So my derivative here, and I know the derivative is 0 here. Now, when the derivative here, when I take L as 10, right, I have negative, this is my derivative here, right? So I'll just write that here. Oops. So my derivative with respect, so L dc over dl, I'm just going to write it again, but I'm going to like simplify it. So that equals that equals 2 minus 800 over L squared. Okay. So that means that dc over dl is 2 minus 800 over 10 squared, which is 100, equals 2 minus, this is just going to be 8, which is less than 0. So I have a negative here. That means I'm decreasing. Now, dc over dl, when L equals 30, equals 2 minus, and this is going to be 800 over 30 squared, otherwise known as 900. 2 minus 800 over 900, which equals 2 minus 8 over 9, which is greater than 1. So this is a min. So I know I have a min when L equals 20. Well, okay, now I solve for the other one. When L equals 20 feet, this is the one I have. So 400 equals 20 times W, which implies that W equals 20 feet. Okay, and then so what I have is that the cost equals 2 times 20 plus 2 times 20, which equals 800 feet of fence. Okay, so I need 800 feet of fence to build a 400 square foot area. All right, 1 to 5, how do we feel about that? So I did a min check. I basically did all of the same steps, except my derivative was a little messier, and I had to deal with this negative bit. Okay, well, and we're going to talk about these more and more. We're going to talk about a lot of these problems, but let's look at one more. Okay. So let's do a fun one. Why not? It's the season to talk about campaign commercials, so let's talk about campaign commercials. So, here's the situation. Both Republicans and Democrats create propaganda that produce benefit to society according to the formula R to the 1/3 times D to the 1/3, where R denotes minutes of Republican propaganda and D is minutes of Democratic propaganda. It costs Republicans $1 million to produce a minute of campaign propaganda, while Democrats pay $2 million per minute of campaign propaganda. Now, if we're going to spend $400 million, what's the most BS we can get for that? Okay? So is everyone on board with this problem? 1 to 5, how do we feel about that? Well, this is another one of these max things, right? So what am I going to do? I think 400 may end up being a nasty number that doesn't come out cleanly. But let's look at it, right? I've got BS equals R to the 1/3 times D to the 1/3. And I've got the cost, right? So the cost is 1 million times Republican commercials, minutes of Republican commercial, plus 2 million times Democrat commercial. That they have unions, right? So Democrats support union labor, things cost more. And they Democrats don't know what anything costs, right? So, you know. Don't look at me like that. I'll be razzing on Republicans too. Okay. So, I've got this type of idea here. And I know that this is going to equal 400 million. Okay. So what I'm trying to do here is I'm trying to maximize output with fixed cost or subject to some cost. All right. So R&D is this. So I've got R plus 2D equals 400. Wouldn't it be nice if I just could divide that? Then I get a 200. Wouldn't that be nice? So let's do that. Let's solve here for R. So R equals 400 minus 2D. That may have been a bad idea, but we'll do it this way. Yeah, because then I'd have an R. I'd like whole numbers. They're nicer. So that means that BS equals 400 minus 2D to the 1/3 times D to the 1/3. So now DBS over DD equals, now I got to do a little chain rule action here, 1/3 400 minus 2D times -2. That's the derivative of the inside. And there should be a -2/3 right there. Yep, there we go. Is there a way to simplify this before I take the derivative? Oh well. All right, so that's the derivative of the first times the second. I mean, it'll simplify eventually because then I'll be able to simplify it there, but I can't really right now. Plus the derivative of the first, the first, 400, minus 2D to the 1/3, times the derivative of the second, which is 1/3, D to the -2/3. And I'm going to set that equal to 0. So 1 to 5, how do we feel about our little derivative there? The 1/3 will cancel. Let's see. When I do this to 0. Oh, when I do this to 0, oh, that's going to work out beautifully. I'll show you why it works out beautifully in a moment. It'll work out beautifully. It looks ugly right now. So set equal to 0 for optimization. Okay, and I get 0 equals 1/3 times 400 minus 2D to the -2/3 times the -2, don't forget about him, times D to the 1/3 plus, oh, this is going to be beautiful. I sound like Donald Trump, don't I? I need to stop that. 400 minus 2D, 1/3 times 1/3 times D to the -2/3. Okay, let's stop for a moment. This is ugly. Okay? First things, those 1/3. Bye-bye. Let's multiply both sides by 3 and get rid of those 1/3. Okay? Goodbye to them. Now, is there anything else that will work out here? So what I'm going to do is I'm going to move this whole thing over to this side. So a little bit of algebra, And I get -2. D to the 1/3. Oh, no, the negative goes away. I get 2. D to the 1/3. 400 minus 2D to the -2/3. Equals, on this side, I would get 400 minus 2D to the 1/3. You see why I said this is going to work out? Because when I multiply both of these by the 2/3, those are going to cancel. times d to the negative 2 over 3. So now I'm going to multiply both sides by d to the 2/3. That's going to move that d over there. And then I'm going to multiply both sides by 400 minus 2d to the negative 2/3. And magical things happen. 2 times d to the 1/3 times d to the 2/3. Look at that. I added the exponents. They're gone. Equals 400 minus 2d to the 2/3. 400 minus 2d to the 1/3. And I say goodbye to my exponents because I add them together. And I say goodbye to my exponents because I add them together. And that's going to give me 4d. That goes over here equals 400. That's going to give me d equals 100. How do we feel about that? 1 to 5. Okay. So I've solved for my thing. So I'm going to go ahead and plug in what r is. So r equals 400 minus 2 times 100, which means that r equals 200. And why is that? Well, we expect that. They're cheaper. Okay. So now I do and then my total BS equals 100 times to the 1/3 times 200 to the 1/3. Oh, nasty numbers. Let's see. I'm going to get 1, 2, 3, 4 zeros out of there. There's just nothing to do there. It's ugly numbers. I could pull 3 of the zeros out. So that's going to give me no, there's just no pretty way to do this. You're going to wind up with an ugly number. Okay, so this is going to give me 10 times 10 to the 1/3 times 2 to the 1/3, 10 to the 1/3, 10 to the 1/3. There's just no easy way to do this. So this is the cube root of 2 times the cube root of 10 which is the cube root of 5 times the, nope, nothing there, times 10. Ugly number. Calculator time, yes. Okay, that's what you wind up with. And how do you know you have a min? Well, the endpoints are d equals 0, bs would equal 0, and r equals 0, making bs equals 0. So I found the max at my one critical value. Okay. So how do we feel about these problems, 1 to 5? Okay. So I gave you one to play with on the quiz. Are there any questions? Okay. So the strategy for these is kind of, let's just kind of write out what we think, how we do this. Okay. So what do we do for these problems? So 1, draw pictures. Find formulas. etc. 2. Identify if you are maximizing output given cost, or minimizing cost given output. 3. Make one equation. With one unknown. 4. Look at endpoints. What's next? 5. Derivative, set it equal to 0. Find critical values. Why are the endpoints 0? Because that's what makes sense. So, can I have negative campaign commercials? Well, okay. Bad question. Can I have campaign commercials that last negative time? No. Right? Campaign commercials last some finite amount, hopefully finite. By tomorrow, hopefully, At this point, you ever get to that point on a test where you don't really care you've been studying and studying and studying so long that you don't actually care what you get on the test? You want it to just be over. Like, you're at this point, if you know enough to get a C, you're okay with that. That's kind of where I think most of us are with this election, right? We've gotten to the point where we care less about the outcome than the fact that it's done. At least, I think that's where most of us in the middle are. I don't know where you are, but that's where I am. I'm kind of in the middle, and I'm like, I don't actually care who wins. I just want it done. I want it over with. I voted. It's done for me. And that's kind of where, but I can't have, negative time on the campaign commercials, right? There's going to be more campaign commercials, or at least 0 campaign commercials, right? So that's why those endpoints are 0. I have to have at least some campaign commercial, or none campaign commercials. So I can't have less than 0 campaign commercials. Okay. So I look at the endpoints, and then I solve for critical. So take derivative, solve for critical values. Solve for critical values. 6. Okay, make sure you have a max or a min. And you can do that however you want to, right? You can take a second derivative and see if it's positive or negative, which will give you concavity. You can look a little bit to the left and a little bit to the right on the first derivative that you already took. You can make an endpoint justification, anything. You just have to do it. And 7, state what you mean by the answer. Okay, 1 to 5. How do we feel about these now? Okay, does anyone have any questions? Okay. So here's what's happening this week, next week. Remember, the test is not this Saturday. It's next Saturday. It's now Monday. So, it's 12 days away. Here's what's going on. Okay, so tonight we did optimization 1. All right. Thursday night, we're going to do derivatives in the shapes of graphs. So we're just going to kind of try to tie that all together. All right, Sunday night, exam review 1. Monday night, optimization 2. Oh, this is going to be more examples and another way to do them. Okay. All right. What is it? It's Thursday during the day is the other one, right? Then it's exam review 2. So this right here is next week. And then Friday day bootleg review. The bootleg, by the way, is in the approval process. Everyone's looking at it. They're trying to find out what they want to mean, and then of course I have to edit it. But the bootleg is in the works. Okay, we got. It's been sent out. It's being looked at. I've got approval for the questions I want to add. We just have to kind of coalesce around the questions that everybody gets for their exam review. And that process is in the works. So we're going to get the bootleg out for you sooner. And then Saturday is 9 a.m. is test 3. Okay. And then the thing that I usually do is Thursday night, I'm moving. So next Thursday, not this Thursday. This Thursday, I'm still going to do 11B. Next Thursday, I'm going to move that to Sunday. So last time I missed the lecture because I was just like, right? And I just totally forgot about it. But it actually worked out better, I think, to do it on on Sunday. So what I'm going to do is I'm going to do that one on Sunday. So Sunday, and I'll move everything back as normal, and I'll make an announcement as everything. But Sunday will be a lecture 12B, and that will be on the AUC function. So that's at 7 p.m. Lecture 11. I'm sorry, this is a lecture. That'll be 12B. All right, are there any other questions? Do we have a web assigned tomorrow night? Yes. I've actually made most of it. I just need to split it because it's this long. And I need to cut half the questions and, put half of them on Wednesday night. I'm sorry, on Tuesday night and half of them on Wednesday night. So I haven't done the split yet, but as soon as I'm done with the split, I'll have it up. There will be a web assign and it'll be on this stuff. I wanted to make sure I got through it all. Are there any other questions? And I need to cut it up. Any other questions? Okay. Well, that's it for optimization. We are coming back to it again on Monday night. I'll let you do some problems and play with it. But remember kind of this big idea. I want to take, things cost something, and I want to make one equation with one unknown. All right.